activity. We do not measure the amount of a material that emits radiation in pounds or by volume, like gallons. That doesn't really mean anything. What's important is not the amount of material you have. What's important is the amount of radiation that's emitted. You think about it, it makes sense. What I care about is how much radiation, gamma or alpha or beta, is coming towards me that it could interact and cause damage to my body. And so we measure the amount of material based on the reactivity of it. And this is what we call Curies. And there's 37 billion disintegrations, or per second is 1 Curie. So you have 37 billion gamma rays emitted per second for a material. You have 1 Curie of that material. Now, how big is a Curie? Well, it could be very, very small. It could be an ounce of material. It could fill half this room. Depends on what it is. So that's why volume and mass doesn't mean anything to us. It's all about the radiation. And by the way, if you have 1 Curie of anything, that's trouble. You've got a lot of radiation. That's a very serious situation. You know, most things are in the microcurie range. All of these sources here are in the 1 to 10 microcurie, very, very small quantities. The becquerel is the international unit of measurement of activity. And the reason I mention it is because there's only 2 countries in the world that use the Curie, United States and Russia, which is kind of odd. The rest of the world uses the becquerel. And 1 becquerel per second, 1 disintegration per second is a becquerel. So you end up with 37 billion becquerels equals a Curie. They're unwieldy units. I don't particularly like them, but you must be aware of them because shipping papers, other documents will be becquerel. And so you have to understand the conversion. Now, in the example that we used with the cesium, the 1 microcurie source, this is emitting 37,000 gammas and betas every second. Which you think, my God, that's an awful lot of radiation every second. How in the hell can you hold that in your hand, Carl? Well, it's because I'm immune to it, and I've lost all my hair, so it's not a health issue anymore. Well, we'll talk a little bit later on, but not all of these gammas and betas are coming towards me. So that's a little hint, preview to come. Yes?
On the unit, does it matter if it's alpha, beta, or gamma?
It's a very good question. So does it make a difference whether it's alpha, beta, or gamma as far as using these units? And no, it doesn't make a difference. It's just the amount of radiation, the number of decays from the material. It doesn't matter whether it's alpha, beta, or gamma. So it works for all. Let's talk about half-life. This is an important concept. And it's something that really becomes very important when we talk about nuclear waste. And one of the biggest issues with nuclear power plants is what do you do with the waste? It's highly radioactive. Where do you put it? Because it's going to last for a long period of time, thousands, 10,000s of years. Well, that's the concept of half-life. Half-life is very simply the amount of time it takes for the radioactivity of a substance to decrease in half. And the best way for me to describe this is through this illustration here. Let's pretend all this red material is radioactive, 100% of it. And its half-life is 1 hour. After 1 hour, half of it is going to undergo decay and become this white stuff. Another hour goes by, and the remaining half of that undergoes decay. So now we're down to 25% of the material we started with after only 2 hours. And this will continue. The material will decrease in half and half and half of reactivity. Finally, we get down to 10 half-lives. We're down to a 0.1% of the reactivity that we started with. And at about that time, we consider it basically reached background levels and not harmful to us. Now, of course, it depends on how much material you start with. If you're talking about nuclear power plant waste, it's going to take a lot more than 10 half-lives to get rid of it all. But for most materials, it's about 10 half-lives and it's gone. So a material that has a half-life of 1 hour, 10 hours later, probably can't detect it. Not a big deal. Now, everything has a unique half-life, ranging from very long periods of time, billions of years, to very short periods of time, like microseconds. Some of these materials are naturally occurring, like uranium-238. We were introduced at the beginning of the class. 4.5 billion year half-life. It's going to be around for a long, long time. Carbon-14, almost 6,000 year half-life, important for carbon dating. If you heard about the technique that you find in old fossils, well, they are able to determine the age based on the reactivity of the carbon-14. It's pretty cool science. Iodine-131, this is something that's not naturally occurring. It's made for the purpose of treating thyroids. And the material is injected into your system. Your thyroid collects iodine, and so that radioactive iodine will go to your thyroid, and it will start bombarding the cancer with beta radiation. And hopefully it kills the cancer more than it kills the other cells, and that's how you treat thyroid cancer. Now, the amount of material they use is all dependent upon the cancer you have, the amount, and I don't know the exact amounts. It all depends on the situation, depends on the person. I'm not a physician or an oncologist, so I don't know the exact amounts to answer your question specifically. But it's high enough that you could take this detector here, put it near your throat, and you could probably detect it. So the question is, does that radiate out of the person's body? It does to some extent, but most of it is pretty localized. And so when the physician treats a patient, they might restrict them to stay in your home and don't snuggle up next to your family and your pets for X amount of time. Now look at the half-life. 8 days, so it takes about 80 days for it to decay to a point where we're not concerned about it. That's a long period of time if you're carrying around your thyroid. But there's also a biological half-life where your body expels it from your system and such. But the amounts they give are very, very controlled. And they've calculated just the amount that you need for that particular treatment. So in general, it's not a problem. Other types of materials have very low, short half-lives, and those are of no use to us. And they exist only because we created them through an experiment or a laboratory or such. But what's important about the half-life is this. The shorter the half-life, the higher the activity. You think about it, it makes sense. If you have a really short half-life, it's undergoing decay very quickly and giving off the radiation in a short period of time. That's bad, because that's more radiation coming at you. And there's a higher risk, health risk. Things that have really long half-life, there's hardly any radiation emitted, and therefore much lower health risk. In fact, uranium-238, 4.5 billion year half-life, is what's called depleted uranium. You may have heard of depleted uranium because it's used in the Gulf War and the Iraqi War. They use it for military munitions at the tip of bombs and bullets and such. They will put the depleted uranium, this pure uranium-238, it's a very dense metal. And it has a unique property that it can penetrate thick steel. And the way it was explained to me is it basically is like a drill. It penetrates the steel and just drills right through it. Very effective. Well, the uranium is, of course, radioactive, but it's also heavy metal. And soldiers will breathe the fractured material. It gets in their system. The heavy metals are bad for you, just like zinc and selenium and lead and so on. And in fact, the chemical aspect the toxicology of the metal is way more important than the fact that it's radioactive from a health perspective.
Are they still using it for ballast on airplanes?
The question is, do they use it for ballast on airplanes? I believe some do. I'm not sure which planes have them, but it was commonly used as ballast. It's used for a lot of different purposes. Again, it's not very radioactive. So from a health perspective, not a big deal. You just don't want to eat it or breathe it, just like you don't want to breathe or eat lead.
We have to watch, we have at our airport, they dismantle airplanes. And we had some contractors who didn't know that they were cutting them up with bandsaws. And then taking them to the recycle yard, and the molecules went off to the recycling.
Yeah, so people get a hold of materials and do various things to them, not realizing that they're hazardous, and chop them up and process them, melt them down. We've seen it all, and it's the ignorance that gets them in trouble. Question?
So, the Fukushima disaster,
So Fukushima had a release of radioactive iodine. So all nuclear power plants, when they undergo a release, will release a few main components, and one of them being iodine. And it is, in general, not a health hazard unless it gets into the food system, which is typically through milk. It falls out onto the grass. The cows eat the grass, ingest it. It gets into their milk. That gets put into the container, and someone buys it, and then they consume it, and now they're ingesting radioactive iodine. And typically not harmful to us as adults for the most part, but for children it can be worrisome. Right, they're a lot younger, their systems aren't as quite developed, and much more dangerous to them than as adults. That's a very good question. So the question was, can you use the mineral iodine to prevent thyroid cancer? So you've probably heard people buying iodine tablets after Fukushima, and I think my father sent me a link to a website that was selling them for, I think it was hundreds of dollars for a packet that had maybe like 2 tablets in it. Okay, so a couple things about this. Yes, it does help prevent you from absorbing the radioactive iodine. Your thyroid needs it every day. So you're eating foods, and you basically have these open sites in your thyroid, and it needs an iodine atom to close up that site. So if you have an open site, you breathe the radioactive iodine, it's going to go right to the thyroid, and it's going to sit there and irradiate your thyroid, and you can get cancer. And I'll show you an example of someone who had that happen to them. So by flooding your thyroid with non-radioactive iodine, you prevent the radioactive stuff from getting in there. That's what the tablets do. So they protect you from only one type of radiation, the iodine, radioactive iodine, and that's it. It's not going to protect you from the gamma. It's not going to protect you from the other types of materials that are emitted from a nuclear reactor disaster. Now, the fact that we live over 5,000 miles from Fukushima, the amount of radioactive iodine that actually made its way here was minuscule. And the fact that people were even remotely thinking about taking iodine tablets, it was ridiculous. And there was no reason, excuse me? You have to have it in your diet. You have to have it in your diet. But from the perspective of protecting from radioactive iodine was not necessary here in the States. And there's only pretty severe exposures where you do need to start taking it. And that's always announced by a public health officer around the nuclear power plant. And they're usually very small areas where people would even be susceptible to it. It dilutes very quickly in the atmosphere. So the question was shorter activity, shorter half-life, higher activity. So is it stronger? The word stronger is a little bit of a difficult concept to, stronger in the fact that it has more radiation. Well, there's more radiation that's emitted in a short period of time. So in that instance, it's stronger. But the fact that it's beta radiation, it's only going to really be harmful if it's in your body, for the most part, or on your skin. But if it was a gas, can't settle on your skin very well, and that's what iodine is. It's a gas. Okay, good questions. Any others? How do you know the half-life of material? Well, you can look in the table I gave you as a reference in the back of your handout, or you can go to the internet. Well, there are a lot of sources for this information, some which are reliable, some which are not. I would not say Wikipedia is probably the best reference for scientific information. And there's a lot of information that's very complicated. The Health Physics Society has probably the simplest way to find accurate information. And this is the website here. It's public access, and I'll demonstrate how you get to it through this link here. We go to their website, and you'll see the periodic chart. And if you're interested in any particular element, let's say uranium, which is down here, you would click on that, and up on the left-hand corner here, we would have select isotope. There's many types of uranium that are radioactive, and so you would select which one you're interested in. And let's say we're going to go to uranium-238, which we've already talked about here. We would select that, and it brings up all kinds of crazy information, most of which you don't need. So ignore it. What you're really looking for is, how does it decay, alpha? Well, and what's the half-life? And because we're scientists and we can't do anything simple, we use scientific notation. And so the E plus 9 means that it's to the 9th power. And so you have to move the decimal place 9 places, and you end up with 4.5 billion years, which we've already discussed. So that is the simplest source you're going to find on the internet. But the main thing is, what's the decay? It's alpha, emits alpha, and what's the half-life here? Another very interesting thing that I've alluded to earlier on was something called decay series. In this example, we're going to pick on uranium yet again. 4.5 billion year half-life. It emits primarily alpha, a little bit of gamma. It decays at something called thorium-234 with a much, much, much smaller or shorter half-life, 24 days. It emits primarily beta and a little bit of gamma. It undergoes decay also because it's radioactive, something called practinium meta-234. Has a 1-minute half-life, emits beta and gamma. And this process will continue. And the half-life will change from very, very short to very long periods of time. And the types of radiation emitted will change depending on the radioactive material. And this will continue. This decay series is quite lengthy. There's radium, there's radon, polonium, lead, bismuth, and we're not done yet. We got to get down to eventually something that's stable, and it's lead-206. So all the uranium in the Earth's crust in the world will eventually become lead in a few tens of billions of years from now. In the meantime, you've got this mixture of all these reactive materials emitting alpha, beta, and gamma. It's a lot of radiation from one material through this whole process. That's a decay series. And the point of all this is that if you were to inhale, let's just take radium-226, one radium-226 atom. If you were to inhale it, get it into your body, or ingest it, over its decay series, as it decays to one thing after another, after another, after another, you could possibly be exposed to 5 alphas, 4 betas, and 8 gammas. That's a lot of damage from just one atom. Now multiply that by a few billion, and you can understand the potential health effects. So you have to protect yourself from ingesting and inhaling these materials. So I always emphasize, if you're going to play this game, you've got to wear your damn respirator. It's that simple. You do that, you've taken care of 99% of the problems. It's very simple. Now, we've talked about what the characteristics are of radiation. And alpha, beta, gamma, neutrons, they penetrate, they don't penetrate your skin, what's internal, what's external. And really, I want to break it down and make it really simple. Radiation is energy. More energy, the more damage. It's that simple. Visible light has very, very small amounts of energy. Alpha, beta, and gamma, a lot more. And you notice the alpha has a lot more than the beta and gamma. That's why it's much more damaging internally. And the neutrons, it varies greatly depending on the types of neutrons. So you got to protect yourself from that energy, and you'll be just fine. And the good news is we can detect it, and then we know we can take action. And we'll talk about action levels here coming up shortly. Oh, microwaves. Microwaves have nothing to do with nuclear radiation. In fact, microwaves are not ionizing. They're not harmful to us, I guess, unless you have certain medical devices like a pacemaker that may disrupt the electronics of that device. They're not harmful to us. They're made from a magnetron. It needs an electrical source to create the microwaves. The microwaves cause water molecules to vibrate. That vibration is friction. Friction is heat. And that's why when you put your wet cat in your microwave, it's going to explode. So don't do that. Question?
What type of radiation is used to sterilize food?
Sterilization of food. We're going to talk about that later on. So any questions? We're all on the same page on alpha, beta, gamma, neutrons, activity, half-life. Well, let's talk about some units of measurement. I mentioned earlier we measure very, very small quantities of radioactive materials in the micro and milli range. So let's talk about some of the units of measurement. Again, we always deal with very, very small quantities typically. The micro, the milli. If we get up into more than that, it's a pretty serious situation going on. Radioactive materials emit radiation in all directions, just like a light bulb emits visible light in all directions. So I mentioned earlier on that this cesium source emits 37,000 gamma rays every second. And you are all just amazed that I could hold this in my hand and still be alive. Well, those gammas are going in all different directions. So the amount that's actually interacting with my body is only a fraction. So that's the good news. Bad news is I can't get away from this. I can't go to the side. It's everywhere, all different directions. Curies, we've already talked about, is the amount of reactivity, the amount of radiation emitted from the material. And we talked about the becquerel, the international unit. So it's just a little refresher. Detectors like this one, the pancake probe, a lot of detectors read out in what are called counts per minute. And this is very simply every gamma, every beta, every alpha that interacts with the detector is one count. And the computer figures out how many of these occur every minute, and gives you a readout. When I turn this on, and I'm just looking at, as I mentioned, background radiation. Give it a few seconds to come up to full scale. And typically, for this detector, you will be in the 30 to 60 counts per minute range. And right now, I'm at 40 counts per minute. That's just natural. Now, what does that number 40 mean? Well, it just means there's 40 alphas, beta, gammas about every minute come through this detector. Is that harmful to you? No, it's background. But what number is it harmful? Well, that depends on what you're detecting. And I can't give you a good rule of thumb. Other than when you double the background, then you probably have something that's radioactive. So I'm at 40. When I hit 80, that tells me I have something that's radioactive, and I need to do something about it. Now, these counts per minute are not the same as activity, because I can't detect all the radiation coming out of material with a little detector like that. That's impossible. And it has nothing to do with exposure. So what is exposure? Well, that's a measurement that's uses the units of Roentgen. Now, Roentgen technically is ionization of air by gamma radiation. Some instruments do detect in the units of milli and micro Roentgen per hour. And we'll talk more about that here in a second. Now, Roentgen is not a measurement of dose or damage to human flesh. Okay, that's just something a detector can measure. So we have something called the Roentgen Equivalent Man. The Roentgen Equivalent Man is a measure of damage to human tissue. And I apologize, ladies, this was developed back in the old days of science when very few women participated, and so the vote came around and it was pretty much 1,000 to 1 for the word man instead of human or person. So it's a Roentgen Equivalent Man, or the REM. Now the REM, as I mentioned, the amount of damage to human flesh. Does not work for cats and dogs. Doesn't work for your pet snake. It's only for people. There is an interesting relationship between Roentgen and REM. Roentgen being exposure, REM being dose. 1 Roentgen is equal to about 1 REM if you're exposed to gamma radiation or beta. Doesn't work for alpha. For alpha, internal exposure, and this is very approximate, the ratio is 1 to 20. So 20 times more damage to you being exposed to alpha than the gamma or the beta, if it's internal. So that's why you got to protect your inhalation pathway and not inhale things that emit alpha. It's 20 times more damaging. During Fukushima, most news reports did not use the REM. Why? Because guess who are the only 2 countries in the world that use REM? United States and Russia. So the rest of the world uses something called the sievert. There's 100 REMs in 1 sievert. So when you're talking in units of sieverts, you're talking about very high exposure. So most of the news reports that you heard used millisieverts, or 1,000th of a sievert. So 100 millirems is equal to 1 millisievert. That's still a fair exposure. Usually we're in the micro range. So some of the news reports you probably heard talked about the first responders or the workers at the plant and what some of their exposures were, and they were well into the millisieverts. And not going to kill them, but pretty high abnormal exposure, definitely. So simple math here, just multiplying by 100, but bad news is you have to do the math. So quick little summary here. We have Curies, the amount of radiation emitted from the material. That's how we measure the amount of a reactive material. We've got the counts per minute, which is what is interacting with your detector. And it's a relative number. It doesn't tell you whether it's bad, good, or indifferent. It just tells you whether you have something that's radioactive or not and about how much material. The Roentgen is exposure in air. And then the damage to us from that radiation is measured in rem. And I'm going to bring these all together in a couple illustrations here. If we have a radioactive source, we measure in Curies. It emits a radiation field. Let's say it's gamma radiation. That gamma is going to interact with your body. Some of it will interact with the detector, which can be measured in Roentgen or counts per minute. The Roentgens can be expressed in terms of rem by that ratio we saw, which is damage to your person. Now, exposure and dose are important concepts that I want to emphasize because they're easy to confuse, and we need to make sure we understand the difference. So another illustration here. We have a radioactive source. It emits a radiation field. Again, we're going to use gamma radiation. All of this gamma is interacting with your body and causing damage. And that damage is accumulating over time. And the more damage, the more health effects, and that accumulation can be either acute, meaning it's going to manifest very shortly, within minutes, days, weeks, or it can accumulate over your lifetime and manifest as cancer 20, 30 years from now. So that cumulative effect is occurring as you're being exposed to radiation. So we try to protect ourselves from the radiation as much as possible and reduce that cumulative effect. All radiation, unless it's for purposes of treatment, we consider basically bad. So this is the exposure. The damage is the dose. Any questions about that? Great. Let's talk about dose rate and dose. Your dose comes from exposure to the radiation over time. Well, the dose rate, which is the amount of radiation emitted over time, which is measured in micro-Roentgen per hour, milli-Roentgen per hour, or God forbid, a Roentgen per hour, which is a very high exposure rate. Over a certain period of time, you multiply those together, you get your dose. Seems like simple math. It's not. It's not something you can calculate by taking your detector, taking some measurements, determining your dose. You can't do it. We use something called a dosimeter, which I will talk about later on here. Now, micro, milli, all these units can get kind of confusing. So I'm going to make it really simple for you. And I have a units mnemonic here, a little memory aid. Micro R, you're okay. Milli R, maybe. R, rethink. So if you're in the micro R range, you're going to be okay. Don't worry about it. When you get into the milli-Roentgen range, you got to start thinking about what's going on. You're not going to die, but you got to be on top of your game. When you get up into the R range, you really got to think about what's going on and think about your objectives, why you're there, and probably back out and bring in the professionals. I'm sorry, this slide is not in your handout. I included it late last night. Yes, Will.
Is that all true for international units as well?
No. No, it would be different. Because international units are 100, a difference of 100 here. So the difference of 100 micro-Roentgens, well, that would be 1 micro-sievert. So I guess in general it would, relatively. It could work. Just understand that, you're talking about 2 orders of magnitude difference. But since we deal with mostly Roentgen and RIM in this country, this works very well. And it doesn't matter whether this is Roentgen or RIM, it works. So just a quick little memory aid there. Now, how much can you be exposed to? Well, actually a fair amount of radiation before we consider it a health risk. And in the United States, and in a lot of countries, we have occupational dose limits that are 5 rem per year. Now this is occupational. Does not include medical exposures, does not include natural background, which you're exposed to all the time. This is on the job. You cannot exceed 5 rems cumulative over a year. And this is found in our state California regulations, found in federal regulations, and everyone who's exposed to radiation has to be monitored with something called a TLD badge, and I'll show you an example here shortly, or some other dosimeter to measure that radiation. When I go to radioactive waste sites for investigations, I have to wear one. I send it to a laboratory every 6 months. They tell me what my exposure has been. The general public cannot be exposed to more than 100 millirems in a year. Now that is from incidental exposure while passing a facility or visiting a facility that has a radioactive material, like a hospital. Hospitals have to control their radioactive material such that you as general public are not exposed to more than 100 millirems in a year. A very, very low amount. Now for emergency workers, fire, hazmat, police, and such that might respond to an incident, they have a little slightly different standard. And the EPA developed these recommendations, not the law, recommendations. These two are the law. And those are really the only, there's very few laws that control exposure to radiation. And it's basically right here. So EPA has recommendations for first responders. If you're performing any activity, you can accumulate up to 5 rems of dose during that incident. Well, what's an incident? Well, it's a few hours to maybe 24 hours, maybe 48-hour time frame. However, the incident commander defines the emergency phase. You can go up to 10 rems if you're protecting valuable property. For instance, you are coming to my apartment and I have a 200-bottle bourbon collection and you want to protect it. Then you can get up to 10 rems. That's justifiable. Thank you very much. If you're saving large populations, protecting large populations, 25 rems is the limit. And then anything above 25 is volunteer only. And you notice there isn't an upper limit there. It all depends on the situation. Now, is 5, 10, 25, what's the health effects of those? Very, very little. It's really a long-term health effect. The chance of getting cancer down the road.